Hey Chemistry, Mrs. KJ here. We're going to go over 7.03, Uses of Nuclear Decay. So have your notes ready. You're going to want to write down everything on this slide. We use radioactive elements, or elements that decay into other elements, for three major purposes. Number one is for food. It adds shelf life to your food, meaning it helps your food last longer. Second reason is geological and carbon dating. So carbon dating is used in organic materials, living things, photosynthetic reactions to help find dates and times. And it's also used for geological, meaning rock dating or telling how old something is. And the third major use we're going to talk about is medicine. It's used for cancer, tumor, and thyroid treatments. And I just fixed my spelling of the word thyroid, so make sure you have that right in your notes as well. There are other uses. It was kind of interesting. I went on to one of the government websites for uses of radioactive elements, and I was surprised at how many there actually are. But these are the main ones. I am going to go over each of these. You do not need to write down anything else until I tell you you need to write it down again. So we'll go through this, and then we'll kind of hit like another section, and I'll tell you to take some notes again. Food irradiation. Food can be irradiated with gamma rays. So this is the Greek letter for gamma, from either cobalt with a mass of 60 or cesium with a mass of 137. For example, if we do this to our milk, milk can last for 3 months without refrigeration. How crazy is that? And the USDA has approved it for actually a lot more foods than just that. So why do we irradiate food? Well, first of all, to prevent illnesses, specifically ones like Salmonella and E. coli. You can preserve it. For example, when the astronauts go on the spaceship, they use food that has been irradiated, so they don't have to worry about the bacteria coming along and getting sick up in outer space. You could use it to control insects. Delay of sprouting or ripening. So especially if you buy potatoes and then you have potatoes that you grew yourself, you'll notice a huge difference. The potatoes that you grew yourself, usually you have them sprouting a lot faster versus ones in the store. So it can delay the sprouting and then ripening as well. And sterilization. Look at this. Some items can be stored for years without refrigeration. So by sterilizing it, they mean they're killing all the microbes, all the bacteria that lives in it, which, if you think about it, especially if you watch the TV shows where somebody gets really sick, like if you watch Grey's Anatomy or House or any of those medical shows, usually at some point they have an episode where somebody is in basically a bubble, right? Or you've heard of the bubble boy, where someone has such severe medical issues that nobody can go in by them. And it even happens on short term. In a lot of hospitals, if somebody has a certain bacteria or if somebody is super sick, we can't have them exposed to bacteria which normally we wouldn't care about. And so they can do this to their food, so they don't have to worry about the fact that they're keeping everyone away from the person, but obviously they still have to eat, so that way they can get food that doesn't have the bacteria on it as well. And this section is from the FDA. So debunking irradiation myths. And you know, I'm guilty of it too. When we think about radioactive, the first thing we think of most times is like Spider-Man or all the comics or everything that people have made science fiction stories out of. But that's not what happens. So there's three sources that we use. We use gamma rays. They also use X-rays. And they use an electron beam. So again, with all this stuff, feel free to pause and read some more. I'm just kind of going over it. So here's a list of foods that you may have eaten that have been irradiated. And how would you know? Well, if you look at the label, it's going to have that symbol and the statement, treated with radiation or treated by irradiation. So you can look through that. And that pretty much sums up our food. So even though it sounds really scary, chances are you've eaten plenty of foods that have gone through it. All right, so our second, if we go back up to here, our second use of radioactive elements that we're going to talk about is carbon-14 dating. So you've probably seen or heard at some point about mummies and how they can say how old they are. What they do is they use the carbon that is inside the artifact to determine how old it is. So bone, cloth, wood, plant fibers, anything that at one point was alive. So carbon-14. Normally we have carbon-12. If you look at the periodic table, the mass of carbon is 12.01. So that tells us that almost all the carbon atoms have a mass of 12, but some of them are a little heavier. In fact, some of them are carbon-14. They have 2 extra neutrons. And the way that that happens is through cosmic radiation. Sounds very intense, and what it is cosmic rays enter the Earth's atmosphere and collide with an atom, creating an energetic neutron. When the neutron collides with a nitrogen atom, because remember the air is filled with nitrogen, a nitrogen-14, 7 protons, 7 neutrons atom turns into a carbon-14 atom. And so you got our neutron capture, the plant absorbs carbon dioxide and incorporate the carbon-14 through photosynthesis. So it's floating around in the air. When the plant does photosynthesis, it takes in some of that carbon-14. When we, or plants, or animals eat each other, then they take in the carbon-14. And then so you keep doing this your whole life. Okay, you're always taking in some carbon-14 with all the regular carbons. But once the organism is dead, okay, then all the carbon-14 starts to decay because you're not taking in more. And it's going to do beta decay. We talked about how there's alpha emissions, beta emissions, gamma emissions in a previous lesson. This one's going to do a beta decay. So that's the big thing. We're continually taking in carbon through everything we eat, and a small percentage of that carbon is carbon-14. Once we die, we're not taking in anymore, and then scientists can go through and figure out how much is left. So, I like this sentence because in this picture it kind of makes it seem like it's happening all the time, but look at this. The ratio of normal carbon, carbon-12, to carbon-14 in the air and in all living things at a given time is nearly constant. Maybe 1 in a trillion carbon atoms are carbon-14. So they're always decaying. Okay, they're always breaking down, but they're always being replaced by new ones because we're always eating, right? So at this moment, your body has a certain percentage of carbon-14 atoms in it. And all living plants and animals have about the same percentage. But as soon as a living organism dies, it stops taking in new carbon. The ratio of carbon-12 to carbon-14 at the moment of death is the same as every other living thing. But now, remember, the carbon-14 is always decaying, and it's not getting replaced. The carbon-14 decays with its half-life of 5,700 years, while the amount of carbon-12 remains constant. So by looking at this ratio, they can do a fairly precise estimate. And I say fairly because it's not like within a year or two. It can be within hundreds of years. And we'll do more with this on the lab. So because carbon-14 has a half-life of 5,700 years, we can only date things that are up to 60,000 years old. However, we can use other elements that also decay through a half-life, such as uranium, to tell how old other things are, like rocks. And now we're going to go into a different type, but they do mention nuclear bombs, okay? And the reason is because now that people have been, well, practicing with nuclear bombs and attacking people with nuclear bombs, I mean, there's a lot of tests that many countries have done. And so that's actually messed up basically the overall samples on Earth. And so in the long run, we might find that this is no longer a way to find the date of things that have previously been alive. All right. Our third thing that we're going over is medicine. So, medical applications used for thyroid disorders, brain tumors, cancer treatments. Here's thyroid imaging showing one with hyperthyroidism versus a healthy one. So you see a major difference. So we can use radiation for diagnostic procedures, in other words, to figure out what is wrong, to kill cancerous tissue, reduce the size of a tumor, and even to reduce certain types of pain. These are common nuclear medicine procedures that use radioisotopes, so isotopes that are radioactive, regulated by the NRC. So yeah, a person's whole job is to regulate this stuff. So certain examples are brachytherapy, gamma knife, iodine treatment for hyperthyroidism, portable imaging devices in dentistry and podiatry, bone mineral analysis. What it's not. Other procedures may use radiation, such as X-rays, or perform functions similar to those of radioisotopes, but do not involve radioactive material, and therefore they're not regulated by the NRC. Okay, so examples of the ones where we're still using radiation, still using the energy and the emissions given off, but it's not the decaying of a radioactive isotope, would be X-rays, MRIs, chemotherapy, mammograms, so a bunch of different stuff with medicine. All right, so we've covered some really good uses. Now there is something else that you need to know about. Where do you live? So I put Minnesota here. Find your county. Where do you live? And what this is if you live in one of these counties with the pinkish, you're at a very high risk of radon. And everyone else is just that high. So the state of Minnesota, very, very important that you know about radon gases. So radon gas causes many diseases, especially cancer. One of the government documents said it's like 20,000 cases a year of lung cancer and other problems from radon gas. And to talk about how dangerous it is, if you have a home that has high levels of radon, it's approximately 35 times as much radiation as the Nuclear Regulatory Commission would allow if you were standing next to the fence of a radioactive waste site. Okay? Think about that. You've seen in movies radioactive waste sites where you never want to go, and your home could be just as dangerous. Okay? If you're in your home, which, you know, you sleep there every night, right? They use the elementary school, but in your home, you're sleeping 8 hours a night, and just 180 days a year, nearly 10 times as much radiation as it allows at the edge of a nuclear power plant. Okay, so there's a lot of really scary things. Now, that being said, radon breaks down in about 4 days, and when you're outside, you don't have to worry about it. But the problem is when it becomes concentrated in buildings, and it just sits there, and that's when you have elevated risks. Your radon levels can be different than your neighbors. So hang on, let's say what is radon? Radon is a cancer-causing radioactive gas. Radon is colorless, odorless, and tasteless. You need to write this slide down. Remember I said there was going to be more notes? Here it is. Write this down. Your radon levels can be different than your neighbors. Okay, just write that sentence down. And it has to do with the fact of how much water is in your soil, what type of soil you have, how your house was built, all that stuff. So your neighbor might do a radon test and be fine, and you might do a radon test and there's something you need to do about it. So the higher the uranium level is in an area, the greater the chances are that houses in the area have high levels of indoor radon. Okay, and that's where these maps are developed from the rock and the soil. But some houses in areas with lots of uranium in the soil have low levels of indoor radon, and other houses on uranium-poor soil have high levels of indoor radon. Clearly, the amount of radon in a house is affected by factors in addition to the presence of uranium in the underlying soil. So where does uranium come from? We'll pick this up in the next recording. So you may have guessed it comes from uranium. So let's talk about that.